Hello everyone. For our tolerancing scenario, we chose the collapsible cup project. So what is GD&T? There are four parts: the symbols, datums, tolerance zone, and position orientation. So symbols are used to represent characteristics such as length, curvature, and concentricity. Datums are reference points on the part where the dimensions and tolerance are related. Tolerance zone is the acceptable variation around the precise measurement. And then position orientation. Position orientation control parallelism, angularity, and linear aspects of the product's position. And on the left is what a common GD&T would look like. So collapsible cup, what is it and what it does? So for the purpose, we wanted to focus on four things: portability, temperature control, environmental impact, and innovative design. So for portability, we want to have the cup easily portable within a compact form. Temperature control, we wanted the inner thermal resistant layer to allow the cup to maintain a temperature over a long period of time. Environmental impact, we wanted to have a cup that will make sure you're using a reusable product that helps reduce single waste products. Innovative design, we wanted a combination of collapsibility and thermostat that attracts customers with a multifunctional product.
Moving on to parts of our collapsible cup, we have four parts: the lid, the second layer, the third layer, and the bottom layer. The lid is for drinking and also closes up the cup. There's also heat insulation in the lid. The second layer is the body of the entire cup. The third layer is also the body and where most of the liquid is stored. And the bottom layer is the cap for the base of the cup and also locks all the layers into place.
Now we're going to cover the GD&T of our cup. On the left-hand side here is the base section of our assembly. We set datum A as the bottom of our base with a flatness callout. This is important because we want our cup to sit as flat as possible on whatever surface we're setting it on. Next, we have a position callout. This is important because we want our inner diameter to not deviate too much so that we mitigate the risk of compromising the integrity of our outer walls. We also have a perpendicularity callout. This is so important because we're going to be adding a piece on top of this, and we want this to be as true 90 degrees as possible so that we have a solid base. And on the right hand side here is the part that goes on top of the base. So we add a flatness callout on the bottom datum A, and this is because if it's not, it risks not sitting properly, and the slider that connects the two pieces not working properly. We also add a perpendicularity callout. This is very important on the inner side since the base goes basically inside on the inner diameter. We want this to be as close to parallel as possible with the base.
In terms of showing the cup in its functioning state, we decided to show the legitimate model that we have, that we 3D printed using basically a sand-based filament that is basically a powder initially, but once extruded out and solidified, it hardens to this kind of almost soft textured like material that we use for our entirety of the cup design. And just to show the working mechanics of our cup, I made a video of it. As you can see, the cup started as its fully stretched out form where you can hold water, and you can now crush it down by basically having the rail system and using it to collapse the cup in a clockwise format. The also added benefit is that we designed the lid itself to be inverted. So instead of lefty loosey righty tighty, it's lefty tighty righty loosey, making it so that when you twist your hands, you're not also twisting the cap off, allowing for easier maneuverability of opening and closing the cup whenever you need it.